right, this is lesson 5 of college algebra. We are still in unit 1, an introduction to sets of real numbers and set theory. Today we're going to define and apply the concept of disjoint sets. A disjoint set has no elements in common. You have to have two disjoint sets. They have no elements in common. So the intersection of disjoint sets would be the empty set or the null set. So the diagram below shows the set A and B as a Venn diagram. And as you can see, there's no overlap. These two sets are disjoint sets. So let's take a look at some examples of disjoint sets. If we define A as 1, 2, 3, 4 and B as 5, 6, 7, 8, 9, 10, then A intersect B would be the null set or null set. So we can say then A and B are disjoint sets. The intersection of all rational numbers and all irrational numbers, in other words, rational numbers intersected with irrational numbers, is also the null set. The intersection of all even numbers and all odd numbers, this is also null set. So these two sets are disjoint. The intersection of all negative numbers and all positive numbers is also null set. These two sets are disjoint sets. If we let C equal the set of X such that X is a natural number less than 20. In other words, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. And we let D equal the set of elements Y such that Y is an odd integer. And we let E equal the set Z such that Z is a multiple of 4. C intersect D, so I'm taking all of the natural numbers between 1 and 2 and intersecting it with all the odd integers would yield excuse me, 1, 3, 5, 7, 9, 11, 13, 15, 17, 19. In other words, all of the odd integers between 1 and 20. If I were to intersect C with E, I want all of the multiples of 4 between 1 and 20. So this would yield 4, 8, and 16. If I want to intersect D and E, I'm intersecting odd integers with multiples of 4. Okay, since 4 is an even integer, all of its multiples will also be even. So if I intersect that with a set of odd integers, then I would get a null set. Okay, number 4 asks us to write C in set builder notation. So we're looking at all of the natural numbers less than 20. So I could say C is a set of elements X such that X is an element of the natural numbers and X is less than 20. This fulfills all the conditions for the definition of set C. Let's write D in set builder notation, number 5. This is the set D is equal to the set Y such that Y, and I want all of the odd integers. So how can I define the odd integers? Well, I need to define another variable, n, as an element of the integers. And then I need to constrain it in such a way that n is only turns out to be an odd integer. So I'm going to multiply it by 2 and then add 1. In other words, I want all the even integers plus 1. And that would give me all of the odd integers. I could also subtract 1. That would also work. Okay, let's write this at E in set builder notation. So E is equal to the set Z. We're going to define the elements as Z, such that Z is equal, well, I want all of the multiples of 4. So 4n, and we're going to define n then as an element of the integers. In this next section, we're going to talk about set complements. So we will define and apply set complements. First of all, a set complement is written as A prime. So this little apostrophe here is written as an apostrophe and read as prime, or you could also say A naught, since we want a complement to the set A. Okay, so this refers to anything that is not in the set A. All right, so let's shade A prime. Okay, so here is A. The universal set is defined by the box, and it intersects with another set B. Okay, I want everything that is in A prime not. So everything that is not in A prime. So I'm going to need to shade not only the U, but also the B, and everything not in A. So you can see that I am deliberately avoiding the intersection between A and B, because these elements are also in A. So that would not be part of A prime. I only want everything not in A. So again, here we have shading A prime. A prime intersect B. Okay, so this would be everything not in A prime. Everything not in A, so I want all of A prime, and I want to intersect that with everything that's in B. So A naught intersect B would be this section of the diagram. Okay, so everything not in A, but also in B. Okay. This is going to sound a little backwards, but we're actually going to go down here next. I want everything that is in B prime, or not in B. So just like I did with A, I'm going to shade everything that is not in B. All right, so I'm deliberately, again, avoiding the intersection because all of these elements, even in the intersection, belong to B, and I want everything not in B. And now I'm going to take B naught, or B prime, and intersect that with A. So I want everything that's in A, but not in B. So that would also avoid the intersection. Okay. Okay, now for this one, I might use several different colors. I want the intersection of A and B. I'm going to do that in pink. The intersection of A and B. And then I want not that, indicated by the prime. So now I'm going to shade A intersect B prime, or A intersect B not. Okay? And then I'm going to intersect that with U, which is the entire square. So that would then be exactly what is in brown, everything except the intersection between A and B. And then finally, let's intersect, or union A and B, but then I want not that. So that would be everything that is outside in the pink. So A union B not, I would take the union of A and B and shade everything that is not brown. All right, let's take a moment to do some practice down here. I'm going to define 5 sets, A, B, C, D, and U. A is defined by 2, 5. B is defined by 5, 7, and 9. C is defined by X such that X is an odd whole number less than 9. And D is defined by X such that X is an even whole number less than 9. And U is the set of all whole numbers less than, and we're going to say and equal to, or equal to 9. And the reason why we need to include that is because B is part of the universal set. U will be defined as the universal set in this particular situation, and B includes 9. So we need to include 9 in the universal set. Now we're going to find the union or intersection, depending on what it's asking for, using the defined sets A, B, C, and D. All right, so A union B would be all of the sets that belong to A or B. So 2, 5, 7, and 9. Now, even though 5 is an element of the set A and 5 is an element of the set B, in the union, we only write it once. For number 2, we want A union C. So C is defined by an odd whole number less than 9. So this, in other words, would be 1, 3, 5, and 7. No, not 9, because we only want the ones less than 9. And then we're going to unite that set C to A. So we're going to include all of the elements in C as well as the elements of A. So this set would be 1, 2, 3, 5, and 7. Number 3 asks to unite A and D. Well, D is the even whole numbers less than 9. So 2, 4, 6, 8. And we're going to unite that set with A, not rewriting 2 twice. So we'll have 2, 4, 5, 6, and 8. For number 4, we're going to intersect A and B, C. So we're going to take the elements that the elements of set A and C, what they have in common. It would appear as though 5 is the only element that they have in common. So A intersect C is 5. Now we're going to intersect B and D. Well, B is 5, 7, and 9. Those are only odd numbers. D is the set of even whole numbers less than 9. So in other words, 2, 4, 6, and 8. Their intersection would be null set because they have no elements in common. It appears as though I have written B intersect D twice, so 8 would also be a null set. Now let's intersect A and D. So we have 2 and 5 intersected with 2, 4, 6, and 8. It would appear as though the only elements they have in common is 2. Now we're going to intersect B and C. So we have 5, 7, and 9 intersected with 1, 3, 5, and 7. What do they have in common? Just 5 and 7. So in B intersect C is 5 and 7. All right, number 9, let's throw a not in there. So I want everything that's in the universal set, so all of the whole numbers less than or equal to 9, but not in A. Okay, so A not would be the set of whole numbers less than 9, but not 2 and 5. So A not would be 1, 3, 4, 6, 7, 8, 9. And I'm going to intersect that with B. So B is 5, 7, and 9. What do they have in common? Just 7 and 9. So the set of A not intersected with B is 7 and 9. Okay, so there we applied set complements. We talked about set prime, and then we applied those to the Venn diagrams, and we also defined several sets and performed those operations of union and intersection, including the prime.